Go ahead.
Okay, thank you. So today I will talk about Succinct k-mer tables in practice. So I am Yoshihiro Shibuya, and it is a joint work with Djamal Belazzougui and Gregory Kucherov. So the context, we have a k-mer counting table where the values of the counters are distributed. So we suppose them to be distributed following a power law distribution. Usually the k-mer counting tables needs quite a lot of space, of memory space to be stored. Our goal is to have a map between k-mers and frequencies without storing the k-mers explicitly, and the map won't be able to answer the queries about k-mers not present in the original set. But as we will see, other solutions also make these assumptions. Another idea is to use the neighboring, so the information about neighboring frequencies to further reduce space. The classical approach is to use a minimum perfect hash function. So minimum perfect hash functions are hash functions, as the name suggests, which map each k-mer to an interval, a continuous interval of natural numbers, which can be used to access an external array with the frequency with the counter information. Note that the external array is, as the name suggests, external, so we have the minimum perfect hash function and the external array to store. Are minimum perfect hash function the only solution? Obviously not. So I wouldn't be here to talk about it today. There are also compressed static functions. So the main difference between minimum perfect hash functions and compressed static functions are that the latter use the memory for the latter depends on the zero order entropy of the data we want to store. So in theory, with skewed distribution where the entropy is expected to be low, they should be much more efficient than minimum perfect hash functions. So we want to apply them to the problem of compressing k-mer counting tables. Lucky for us, there are some implementation. There is one implementation available for compressed static functions, the one made by Genuzio and Sebastiano Vigna, implementing the Stats4j child package. Unfortunately, this solution uses Huffman encoding, so the space, so there is a lower bound of 1 plus the entropy on the space. But as we will see in this talk, by using Bloom filter, we can get near the lower bound of the entropy for very low entropies. Additionally, as we said before, we also want to use the information about neighboring frequencies. So in order to do that, we had the idea to use minimizer to bucket neighboring frequencies into buckets, and then only save one representative per bucket, which can be the minimum or the most common counter for that bucket. So in order to test our ideas, we implement 4 different methods. One is simple, so the first one, which, as the name suggests, is very, very simple because we just apply the compressed static function to the k-mer counting table. The second one is Bloom. So in order to reduce the space to break the lower bound of the implementation of compressed static function, we use a Bloom filter to remove the most common, so all the k-mers which have the most common frequency in the spectrum. M+bloom, we add the idea of bucketing frequency by using minimizers. And finally, multiple, we use multiple minimizer lengths to do recursive, to bucket recursively the frequencies by adding a new label, let's say, so a collision tag for the buckets where there is a collision. So let's start with Bloom because simple is, as I said, is quite straightforward. So I think I will skip this slide because I have a very nice graphical representation, but the important thing to remember here is that we choose epsilon to have a number of false positives from the Bloom filter almost equal to the number of light items, so the total number of k-mers with the frequency different from the most common one. Yes. So graphically, we have a k-mer counting table. We compute the k-mer spectrum. So the heaviest element is frequency equal to 1. So all the k-mers, all the other columns, so all the other k-mers with frequency different from 1, I will call them light items, and I will insert it into a Bloom filter. Then I will take the heavy items, so the k-mers with counter equal to 1, and I will find the false positives. And finally, I take the light items, the false positives, and I compress them using the compressed static function. So in the end, my data structure will be made up of a Bloom filter, a compressed static function, and I will call it Bloom plus CSF. So next, m+bloom. So the idea is just to first try to filter the frequencies by using a bucketing strategy, and then in the Bloom plus CSF from the previous step, I will use it as a black box now. I will store the k-mer counting table, but I will for each k-mer I will assign to it the difference between its frequency, its true frequency, and the value given by the buckets. So at kill time, I will retrieve the value given by the bucket and add to it the delta given by the Bloom plus CSF data structures to retrieve the true frequency. So graphically, we have again our k-mer counting table. Now the array is a hash table and not a Bloom filter. So we start by bucketing, so the k is equal to 3, we use m equal to 2, so the minimized length is 2. We bucket the first frequency to the third bucket. We do this again for the second k-mer. Finally, we have this bucketing. As a representative, we will choose the most common item in each bucket, so the red frequencies. We put them into the bucket as the representatives, and then we store the whole array using Bloom plus CSF. Then we filter the table, so we will generate another table with the differences. So for example, the first k-mer has a frequency of 4, and we compute its bucket is also 4, so the difference is 0. We make the same thing for all the k-mers, and we store everything into a Bloom plus CSF. So our final structure will be made of 2 different Bloom plus CSFs. Finally, multiple. So we have multiple minimizer lengths. So we start with the minimum one. We bucket the frequencies, but now instead of choosing one representative for each bucket, we can also have a collision if we have 2 different frequencies in the same bucket. At each step, so given for example, the first layer, we filter out all the colliding k-mers and then reapply the method with the next minimizer length and so on and so forth until we reach the last minimized length, which is also k, and by definition, if we have k as a minimized length, we won't have any collision. So the final layer is some sort of catch-all data structure. So example with m equals to 2. So here I will only show you the case with only one m, 2m, where the last one is k. So we have again the same bucketing of the previous case. So for example, in the first row we have 3, 3, 6, so we have a collision. So we replace it with a new label saying that in the bucket there was a collision. We filter the table, taking all the k-mers, the colliding k-mers. And now, because the next minimized length is equal to k, we stop, but theoretically speaking, we can go on so forth until if we had multiple minimized lengths. And okay. And finally, we apply a simple CSF, so not a Bloom CSF, a simple CSF to all the layers. So all the code have been implemented in Python 3 with sub-processes called to the Java code, and we tested the method on the Succinct strain of Escherichia coli for k equal to, so for 4 different cases, you can see on the slide. So for k equal to 12, so the red line is the true entropy of the original k-mer count table. So our method seems not to be very competitive to the simple method of applying simple CSF, but they are better for bigger case, so for increased skewness. By the way, for multiple, the minimized lengths are written next to k, because it didn't fit on the column, the x-axis. So for k equal to 18, we have even better compression. For k equal to 21, our minimizer-based solution, so the green columns, which correspond to m+bloom for m equal to 16, 15, and 14, and multiple, the minimizer lengths given at the top, can even beat the theoretical entropy of the dataset because of the minimizer bucketing. So this is a hall of fame of all the methods, so the best results for all the methods. As you can see, simple CSF cannot go below 1.2 bits as we expected from the Huffman encoding. So to finish up, what should one remember? So CSFs can be applied to the problem of compressing k-mer counting tables. Bloom filters can help in the case of low entropies, and bucketing can help again and give even better results. So future directions. So as you might have seen, as you might have noticed at the beginning, it is a work in progress, so we don't have time benchmarks for now. We will also probably need to apply the methods to more datasets, and probably we also try different minimizer orderings to select the best one for multiple. But there are also many other things we can do, because we can, for example, combine different methods together. And that's it. I finished.
Thank you. Thank you very much for your talk. Again, I'm waiting for some questions. In the meanwhile, I want to thank Karel that is answering questions in the chat. So I'm inviting now the question for Yoshihiro. I'm going to wait a little bit more than last time because after that, okay, so do you have some false positive rate?
Some false positives rate for the Bloom filter, you mean?
I assume so.
I think yes. Yes, the false positive rate is computed. So the Bloom filter is dimensioned by taking so we want a number of false positives almost equal to the light items. So we take epsilon equal to it should be the reciprocal, so k minus k0, so the light item, the number of light items, so the number of k-mers with frequencies different from the most common one, divided by the number of k-mers having the most common frequency. And this is because it will minimize the memory of the Bloom filter plus the CSF.
Okay, thank you. Are there any more questions? So there's been no additional question in the meanwhile. So I thank you again very much.